Okay, welcome back. That is part B of our lecture on classification. And we are ready to move on to two new methods. The first one is linear and quadratic discriminant analysis, and the last one is KNN method. So what I assume is that you've already seen part A, because I'm going to use almost everything that has been used before here. So if you fail to watch part A of this video, I urge you to go back and start working on that, because if you just started from here, it doesn't make that much of a sense. Please go back and finish that part before coming here, okay? I assume you now know what happened in the previous session. One thing I want you to remember is that when we ran our model based on lag 1 and lag 2 and lag 3, we found that none of our variables in our GLM fit was significant. Remember that none of them were significant. So let's try something else. Let's try to get rid of everything but lag 1 and lag 2, because lag 1 and lag 2 at least shows some promises here, some promising results here. The p-value are bad, it's around 30%, but it's not as bad as 90%. So let's keep that and see what will happen. So I rerun everything we had before based on this new case. So I just changed everything to lag 1 and lag 2 and want to see what will happen. So let's look at the p-values. The p-values are not that significant either, but at least our error is 44% now. Before that, it was we found that on our test set, the error was more than 50%. The error was more than 50%. So flipping a coin gave us a better thing. So here, what we found is that lag 1 and lag 2, although not that significant, they do a pretty good job in prediction. They can predict 56% of our test data, which is not bad at all. That's a very good prediction, and actually, if that's on a real data, that can help us a lot. So, in the next sections of this lecture, I assume we are working with lag 1 and lag 2 because it gave us a good test error on our logistic regression. So here I'm going to work with a linear discriminant analysis. Linear discriminant analysis, in short, is called LDA. In order to use that, it's very, very important to use library mass. We need that library, so let's load it first. Using linear discriminant analysis is almost the same, if not exactly the same, as using GLM fit. The only difference is when you do predictions, it directly gives you ups and downs, so you don't need to manipulate your data and define a new and work on direction to change the values based on probability more than 50%, because it already classifies that. So that's a good thing about it. So let's see how it works. So let's put everything in our LDA feed. That's the name of our, this is the name of our variable. LDAs need LDA. That's very intuitive. You use LDA. You work with direction. You just want to predict direction for it, right? You just want to have predictions on ups and downs. So your response variable was direction. In your homework, that was MPG01, but you needed to predict that based on lag 1 and lag 2. What data do you want to use? The data you want to use is S-market, but you only want to use the subset of that is training data, right? So let's run it. So let's see what that creates. So LDA fit have some means for different values that make sure it splits your data based on lag 1 and lag 2 and say, okay, I classify it to lag 1 when, for instance, I classify it to lag 1 as up if yesterday was slightly negative, the previous day was slightly negative as well. I classify it as down if lag 1 was slightly positive and the mean of lag 1 was slightly positive. So let's look how it does it. So let's plot it. Let's plot LDA fit, and it looks like that. That's how it categorizes downs and ups, okay, based on lag 1 and lag 2. That's a schematic thing that shows what's happening here. So now, as always, we want to have the predictions on our training. We have our training based on our training data. That's what we did here. Well, at the same time, we want to use our test data to validate it, right? That's always our point. So let's do our predictions on our test data. So LDA predictions for us is predict, as always, predict. What is the model you want to use? Of course, LDA fit, right? That's the model I'm going to use because that's where I ran my LDA function on. What is the data I am going to use? I want to use a new data, and my new data is the same as S-market data. The only difference is that it used the test data. Okay. See the similarity of prediction, predict. See the similarity of this function and the function you had for GLM. They're almost the same. So if you understand one of them, you know all of them. See, we wanted to work on new data, which was test data, right? So that's exactly the same thing. So let's run it. So our predictions are there. In contrast to logistic regression, when you were only given the probabilities and you needed to assign probability more than 5% to ups and less than 5% to downs, LDA classified them from the beginning. In order to have access to that, we should see what it first creates and see what are the variables you see. So let's look at the data frame of that. Let's look what LDA predicts. But instead of looking at everything, if I just press the enter now, it will show me all the variables. I don't want that. I just want to show a snapshot of that. That's why I ask you to only show me the first 5 points on it, okay? The first 5 observations on it. And as you can see, the first 5 observations in this class has a variable class that gives ups and downs. Thanks God, because we don't need to reclassify it as logistic regression and use an if-else to give up and down. It already classified them as ups and downs. These 5 data were all ups. Okay, so we only need to compare the variable class of LDA prediction with our reality. So remember, in logistic regression, I defined direction test, which was the subset of ups and downs which were related to my test data. I'm going to use the same thing, and so I'm not going to redefine that. That was actually a market of direction for my test data. Look up here. So I'm going to use the same thing to make the prediction errors. I'm not going to reinvent the wheel. It's already there. Why should we bother? So let's see how well our model is doing by looking at the table. Our table uses our predictions. And remember I said in this variable class, it already did everything. So let's just use that. So you use $class. For LDA output is always that. And we want to compare it with the direction test. So we do that. 111 times it predicted correctly, and 141 times it predicted incorrectly. But if you want to run the table, I should have put comma here. So let's look at the confusion matrix here. So let's see where those 111 false and 141 true cases came. 35 times it predicted down, it was actually down. 106 times it predicted up, and it was actually up. If you sum them up, that is 141 times that it was true. And 35 times it predicted down, it was actually up. And 76 times it predicted up, it was actually down. If you sum these two numbers up, you have 111 false. So let's see how big that error is, or how big our accuracy is. So let me do both of them. So we want to find the average of times that class was exactly equal our direction test. That is our accuracy. It was 56%, which is almost the same as what we got before, right? 56%, almost identical. So our error would be the cases that they are not the same. So that is my error. When I say it's not equal to that, that is my error. So my error is 44%. It's not bad at all. It's very good, actually. So if you want to repeat these things for quadratic discriminant analysis, you just need to change LDA to QDA, and you're done. So let me do that. Quadratic discriminant analysis is called QDA. Let me copy paste everything I have there. Just change LDAs to QDAs. Okay, so let me, no, this Q should be small letter. So QDA fit, QDA prediction, QDA fit. I am just changing everything to QDA. I just want to show you how easy it is. So for your homework, if you wanted to do QDA and you already had LDA, you just needed to change L's to Q's. That was that easy. So let me run it again. Voila. QDA slightly outperformed the LDA, and that shows it's slightly nonlinearity there, and that is no surprise that our logistic regression worked well. So that suggests that our QDA, even on our test data, outperforms everything that we had so far. So we are done with the first two cases here. We are only left with one more classification method, which is called the KNN, which is called K nearest neighbor method. In order to use that, it's vitally important that you use library class. If you don't use that, you cannot run KNN method, okay? So remember, for LDA and QDA, you need masked library, and here you need library class. Require and library are the same thing. If you write it, it understands what it has. So let's see what KNN does, as always. So KNN has some training set. Thanks God, it has a test set there. It needs the I explain what CL is in a second. K is how many nearest neighbors you have, and I suggest you always set your probability to false. That way you guarantee that if you repeat that experiment over and over again, nothing will change, okay? Because it's not dependent on the seeds, the error seeds. The CL here is our response variable. Okay, so our training set, excluding our response variable. That means our training set is our training independent variables. Test is our test independent variables. CL is the outcomes of our training variables. So CLs in this case, in these examples, are ups and downs. Train set is the lag 1 and lag 2 of our training set, and test here is lag 1 and lag 2 of our test set. Okay, so remember that CL here means are ups and downs here. So if you are working with any problem, CLs are the outcomes. Training are the independent variables, not the outcomes. Okay, so let's work on it. Let's define it. In order to define it, you should, it's easier to attach your data first. So let me attach it. Smart. So I attach it. So now R understands direction, lag 1, lag 2, and so on and so forth. And here's what I want you to do. Define a variable. You can call it S-lag. I just called it S-lag. And bind every variable that you want to put there. So all your independent variables. So that is bind all your independent variables. It's not your responsibility, it's your independent variables, okay? Be very careful about that. And remember, it says training data. It should be one variable. That's why I binded that and created a matrix of that, okay? So that means there are x-lags of x-lag is a matrix that has lag 1 and lag 2 inside it. So let's see how our prediction for KNN is doing. The name of the function is KNN. Look at here, it says introduce to me the training data. Okay, my training data, which are our independent variables, are S-lag. But which part of my S-lag? Only the training part of it. My test set is X-lag, only the test part of it. So remember when I wanted to do the same thing earlier, I put comma there to make sure I have everything else coming there, right? I just want to have test data with all its attributes. Here I want the test data with all the lags it has. What do I want to predict? I want to predict the variable direction. That is my output. But on what? Only on the test set. Sorry, only on the training set. What K do I want to have? Let's fix it to 1. We can change it as much as we want. So we have our predictions. I screwed somewhere. Let me see where. X lag of, did I run that? Okay, so let me check if I run it. Okay, if I ran it. Error in default training. Okay, so there is something wrong with my direction. Oh, I'm sorry. Direction is a one-dimensional variable, so it doesn't have any attribute. It's just one dimension. Okay, so that was the problem. Here, X lags had 2 dimensions, lag 1 and lag 2. That was, I wanted to look at everything there. But direction was just ups and downs. It's a one-dimensional variable. I shouldn't have put comma there. Okay, good. Now we have the predictions here for KNN. Now we can easily compare it with what we could get from our direction test. So that is as easy as that. So that KNN prediction. Oh, I forgot to, I'm sorry, I had to fix the probability to false. Okay, perfect. So let me run it again. Okay, so I want to check the KNN predictions versus the direction of my test data. I have 126 truths, 126 falses. So let me have the table. Let me see how it looks like. So 43 downs predicted perfectly, 83 times up perfectly, and the rest was predicted incorrectly. So if we just look at the mean of my correct predictions, I just do that. I just put if they're equal, anytime they're equal, it will be counted to 1. So 50%. That is very funny because our error and prediction is just 50%. That means it's exactly the same as flipping the coin. So for K1, it's exactly the same as flipping the coin. Let me change it to 10 and see how it goes. 10 is even worse. So we shouldn't have gone that far. Let me change it to 3. For 3, yeah, if 52.7%, maybe 2 and 4 would also work. So I just changed K, see? 2 was 53, is slightly better. Okay, so K2 is the optimal one. Maybe K4, depending if we change the seeds, it may change it slightly, but it seems like, yeah, it seems like 2 is the best one. Okay, so K nearest with 2 Ks are the best one. So what we learned from here, so let's review what we had earlier. So we started with the logistic regression line. We showed how we can divide our data into test and training, how we can call it in regression line with subset, what adjustment we need to do in order to change the probabilities to the values we want to compare our test data with, how to find the accuracy percentage and the error percentage, how to use library mass to do LDA and QDA fits, linear discriminant analysis, how to work with KNN method. So that is one of my favorite lectures because you have all necessary tools to deal with any classification method. If you came across a new data set, the only thing you need to do is to change the variables. For example, you need to bind something new. Your outcome would be slightly different, but anything else is exactly the same as before. So I expect you, if you're working on your projects or homeworks and you are dealing with classification methods, just change the ones that are necessary. For instance, if your outcome is 0 and 1, you just need to change that to 0 and 1. If your outcome is MPG 0, it's not direction anymore, just change that to that. And everything else is as easy as that. You shouldn't spend too much time. If you have problems dealing with that, please contact me. And usually you can easily solve them. Okay, it was nice teaching you this lecture, and I hope you've had fun with it.